Hello guys, my name is Muhammad Nasr Saiful Islam. I am a student from Department of Physics, the Institut Teknologi 10 November, Surabaya. I am a part of the Basic Physics Laboratory Assistant team for electricity and magnetism. On this occasion, I will explain the experiment on solenoid magnetic field. So, electromagnetic induction. Electromagnetic induction is a phenomenon in which a change in magnetic flux with a conductor induces an electronegative force or EMF in the conduction. That a principle was first discovered by Michael Faraday, who stated that induced EMF is proportionally to the gain of the change of magnetic flux over time. Mathematically, Faraday's law is expressed as epsilon is same with negative n delta flux per delta t, where is epsilon is induced EMF or electromagnetic field and its number of turns or coils, and delta t is magnetic flux in Weber. In the context of this experiment, the magnetic flux is generated by solenoid carrying an electric current, which is produced a magnetic field around it. The strength of the magnetic field inside of the solenoid depend on several factors, such as number of turns, length of solenoid, and the current flowing through it. Theoretically, the magnetic field at the center of solenoid can be calculated by using following equation, where P is the same of mu0 E n per L, whereas P is magnetic field at the center of the solenoid in Tesla, and mu0 is permeability in free space by the 4P is pointed stand by the means -7, and its number of turns of the solenoid, and I is electricity flowing through the solenoid in ampere, and L is length of the solenoid in meter. Okay, the direction of the magnetic field in the solenoid follows the right-hand rule. This hand-collected experiment will include the number of turns of solenoid, electricity, and the strength. The length of solenoid from the end to the end. The measured magnetic field strength. Okay guys, the tool and material used in the experiment of solenoid consists of Gauss meter, one set, two solenoid in 500 and 1000, and then is 9-volt adapter, one piece. Then is 8 compass. There is just in solenoid like this compass. And then is one power supply and one set cable like this. Okay, the methodology and experimental step. Step 1, place the compass in the solenoid mode. Just like this, you can see it on 1000. This compass is already placed. Okay, step 2, connect the power supply to the PLN voltage source or AC source by 220 volt. Then connect it to the solenoid set as current source. In that case, I already connect to the PLN source. Just can put on active like this. Set on the current source by maximize the voltage. You can see the maximize the voltage. You can then adjust the where the voltage is this. In this case experiment, I will use 1000. Just you can see. Then I will connect it with power supply, red cable in the red source, and then the black cable, the black plug. Then I will connect it at the solenoid. You just can see. Just put on, plug in on the right side and the black side like this. Yet it's finished. You can already set on the magneticity field. Okay, what's next? Next is step 3. Record the number of turn of the length of the solenoid. Ask the assistant to show. In that case, the length of the solenoid is 12 cm. And then connect the 9-volt adapter to the PLN voltage source, all AC 220 volt. Then connect it to the Gauss meter. In that case, adapter 90 volts like this, you can just connect it to the PLN source. Yeah. You can just connect to the Gauss meter in this hole, like this black hole. Yeah, you can just plug in. Then set an active Gauss meter like this. Tap. Yeah. You can see that the Gauss meter is already set active now. When you start to turn on, the Gauss meter will calibrate position of the sensor in an area where there is no magnetic field. There's like this. This is no magnetic field, just count on what the value is. On millitesla, this magnetic field in this place is 0 milli-Tesla. Okay, if it's calibrated, the Gauss meter will show the magnetic field value measured by the sensor units of millitesla, measured by the sensor in unit. Then, step 7, the set current in the power supply to the 0.1 ampere. Observe the change in compass direction due to the influence of magnetic field solenoid. Okay guys, in that case, I will set out the power supply to the 1.0 ampere. As you can see. Oopsie. Just correctly measured. There. Okay. Okay, that's it. It's already that is 0.1 ampere. If you can see that on solenoid the compass will already turn, whereas the directly of the magnetic field in the solenoid is already changed. Its effect of the current activity. Okay guys, then step 8. Insert the sensor into solenoid. Select the side where the magnetic field measured by the solenoid is positive. Okay, in this case, the positive side is on this directly side. Just measure it, it's already dead like this. You can see is the center of the solenoid. You can just plug it into this hole. Nah. Okay, just like this. As you can see, just this is the watt measure magnetic field of the solenoid. Okay, then move the sensor along the solenoid, observe the chain of magnetic field on the Gauss meter, and record this isolated magnetic field value that appear of the result of data. Okay, just move on the set like this. You can just place it on the first on the hole, just like this. As you can see, this is changed how much magnetic field on this area. The value is just 0.71 millitesla. Wow, this is actually how much is this? Okay, then perform the step 7 and 9 with different current variation, and then you can just value this, how much the current size change for magnetic field. And then perform the step 7 to 10 with the different solenoid variation. You can use 500 solenoid or 1000 solenoid. You can just see how different the magnetic field they are. Okay guys, that's right there.
So, next we will discuss the experimental data of solenoid magnetic field. In this data table, you need to perform measurement 5 times, with current ranging from 0.1 to 0.5 ampere. The table also includes column for magnetic field value, and then the number of turn and the length of coil. Similarly, you will create similar table for the variation in the number of turn by 1000 turn. Next, how do we obtain the calculated value? Here we have 500 turn, current of 0.1 ampere, length of 12.5 centimeter or 0.125 meter, magnetic field value of 0.479 millitesla. What are we looking for is theoretical magnetic field and its error. To find theoretical magnetic field, you can use the equation by mu0 times current times number of turns and divide it by length of the coil. Substituting the value, we will obtain theoretical magnetic field of 0.5024 millitesla. To find error, subtract the measured value from the calculated value. Divide by a calculated value and multiply it by 100%. Here we have obtained an error value by 4.58%. In calculation table, you only need to add additional column for theoretical magnetic field and error value as follows. Then you will create similarly for other. For discussion, then number 1, explain data result of your data analysis. Number 2, compare the magnitude of the magnetic field in each current variation in the measurement. Number 3, compare magnetic field magnitude between measurement and theory. Number 4, how big is percentage error in your data and explain why. Number 5, what affects the magnitude of magnetic field in solenoid. Number 6, explain the effect of solenoidal magnetic field on the change of compass direction. Number 7, explain how magnetic field can form around the winding wire. Number 8, explain how a change in direction of magnetic poles around a solenoid can occur. Number 9, explain the right-hand rule and its interpretation in the experiment. Is it in harmony? Number 10, explain what physics happened during your experiment, relating it to the theoretical basic you list in chapter 2 in detail. And lastly, number 11, what are error factors of your experiment? Okay, that's all. Thank you.
So the direction of the magnetic field in solenoid follow the right-hand rule in data collected in this experiment will be included the number of turns in solenoid, the electricity current strength, the length of the solenoid from the end to the end, and the measure of the magnetic field strength. Okay, that's all guys. For the next video or other explanation you can access by the channel YouTube of Laboratorium Fisika Dasar ITS. Okay, goodbye guys.